Last time we were graphing rational functions, they were graphed by using the parent function of 1 over x and then using transformations. Today is going to be a little bit different. We're going to be graphing what's called non-hyperbolic rational functions, and they are going to be when you have variables in the numerator and the denominator. So that's going to be a little bit different. These graphs, unlike the ones we did before that only had 2 sections, may have 1 section, 2 sections, 3 sections, or even more. The way we're going to graph them is by following a whole bunch of steps that we're going to go over together. Then we're going to practice some of the parts, and then we're going to graph some of these graphs. So how we graph them, very first thing we're going to do is factor the numerator and denominator. So this might be factor by grouping, the AC method, which we used to do guess and check, so this is now AC method, or difference of squares, difference of cubes, sum of cubes, and GCF. So what we're going to do on this page is we're going to work one example all the way through the different parts. So here's an example of a function that would have variables in the numerator and denominator. So y equals x squared plus 3x minus 10 over x squared minus 4. So our very first step is factor the numerator and denominator. The numerator, we of course first want to check to see if we have GCF, which we don't, and then we have 3 terms, so we would factor that by AC method. So we need something that multiplies to 10x squared but adds to 3x. That would be positive 5x, negative 2x. So we'd have x squared plus 5x minus 2x minus 10. Take out a GCF here, we have x times x plus 5. Remember, we have to match here, so we have x plus 5, which means we'd have to divide out negative 2. So we'd have x plus 5 times x minus 2. So the numerator becomes x plus 5 times x minus 2. The denominator does not have a GCF, and it has 2 terms. It's going to be difference of squares. So we're going to break down the x squared, that gives us x, break down the 4, that gives us 2. So it would be x plus 2 times x minus 2. So once we have that factored, then we're going to move on to the next step, which is discontinuities. Step 2, discontinuities. Discontinuities are actually x values. So we're going to end up listing x values that are restricted from our domain. There are 2 types of discontinuities. One type is holes. The other type is vertical asymptotes. So a vertical asymptote is what we consider a non-removable discontinuity. It has to stay a part of the graph the whole time. A hole is what we consider a removable discontinuity, and you'll see why it's removable in a moment. Holes are created when you cancel a common factor from the numerator and denominator. So if you go up to our factored function here, you see that we have x minus 2 in common from the numerator and denominator. So we actually cancel those out, which is removing that x value, and we write our new function y equals x plus 5 over x plus 2, and you can see that we removed x minus 2. So we have a discontinuity at, if you set that equal to 0, add the 2 over, x equals 2. So we have a discontinuity at x equals 2. So these removable discontinuities occur at the x value you canceled. So here is one, x equals 2. But then, after that, you will need to find the ordered pair for the whole by subbing the canceled x value into the new simplified function. And then we will graph these as open circles. So x equals 2 is our discontinuity, but the whole actually occurs at 2 comma, then we plug 2 into our function, so y equals 2 plus 5 over 2 plus 2, so that is 7 halves. So that becomes our y coordinate of our whole. So we have a whole at 2 7 halves. Oh, guess 2 plus 2 is 4, isn't it? Darn it. So 2 7/4. This is going to go on our graph as an open circle. Non-removable discontinuities are vertical asymptotes, and those are going to be at the x values that we set the denominator equal to 0. So we find vertical asymptotes by setting the denominator equal to 0 after we have canceled. So on our new simplified function, you take the denominator, x plus 2, set it equal to 0, subtract the 2 over. So x equals -2 is the vertical asymptote and also a discontinuity. So vertical asymptotes are at the x value, these non-removable discontinuities, at the x value where the denominator equals 0. After you've canceled. Once we have our discontinuities, those go directly into our domain. So the domain is going to be all real numbers except for the x values that are wholes or vertical asymptotes. So our domain is going to be all real numbers except the one that we had to leave out for the whole, which was x equals 2, and the one we had to leave out for the vertical asymptote, which was -2. Next step is horizontal asymptotes. Horizontal asymptotes are found by comparing the degrees of the numerator and the denominator. And when you do this, you're best to start back from the original function to do that. So use the original function. So there's 3 things that can happen when you compare the degrees of the numerator to the degree of the denominator. The numerator's degree can be less than the denominator's degree. The numerator's degree can be equal to the denominator's degree, or the numerator's degree can be greater than the denominator's degree. So if we look at our original function, y equals x squared plus 3x minus 10 over x squared minus 4, the degree is found by the highest exponent in that polynomial. So we're just looking at the numerator for now. The degree would be the highest exponent, which is 2. So the numerator's degree is 2. If we look at the denominator only, x squared minus 4, the highest degree there is also 2. So the numerator is 2, the denominator is 2, and you can see that those two things are equal. So in our example, we are going to be doing this type of horizontal asymptote. More on that in a moment. If the degree of your numerator is lower than the degree of the denominator, then you're going to have a horizontal asymptote at y equals 0. If the degree of the numerator is bigger than the degree of the denominator, you're going to have no horizontal asymptote. What actually happens there is that you will have something called an oblique, or sometimes called a slant asymptote. Now, we don't worry about those in Algebra 2, but in your next math class you will probably learn how to find the equations for those asymptotes. For now, just know that there's no horizontal asymptote. So back to the kind that we have in our problem, if the degree of the numerator is equal to the degree of the denominator, you're going to have a horizontal asymptote. And it's going to be at y equals, we have to put two numbers over each other. We're going to take the leading coefficient of the numerator divided by the leading coefficient of the denominator. Now remember that the leading coefficient is the number that's in front of the variable that has the highest degree. So if we go to our problem here, our horizontal asymptote will be at y equals, the coefficient of x squared in the numerator is 1. The coefficient of the leading term in the denominator is also 1. So we have a horizontal asymptote at y equals 1 over 1, which simplifies to y equals 1. Now these have to be in that form. They have to say y equals and then a number. These are going to go onto the graph eventually when we get to that point as dashed lines like they did when we did our rational functions yesterday. X-intercepts, that's our next step. We find x-intercepts by setting the numerator equal to 0 after we have canceled. So x-intercepts need to be written as ordered pairs. So there's going to be a number in the x spot and a 0 in the y spot. So for our example, remember that after we canceled, our new function was y equals x plus 5 over x plus 2. So we find x-intercepts by setting the numerator equal to 0. So we do x plus 5 equals 0. Subtract your 5 over. We get x equals negative 5. So our x-intercept would be at negative 5, 0. I'm going to skip over number 6 and go to 7 for the y-intercept. To find the y-intercept, you're going to substitute in 0 for x. And those also need to be written as an ordered pair. So in a y-intercept, we're putting 0 in for x, so it's going to be 0, comma, some number. But going back to our example we're working with, we would have y equals, we're going to use our simplified form, so it will be 0 plus 5 divided by 0 plus 2, which gives us 5 halves. So our y-intercept will be at 0, comma, 5 halves. Once we have all of that information on our graph, we can use an XY chart to help you locate other points on the graph. Using the table feature of your graphing calculator is helpful, and also creating a separate XY chart for each section of your graph is also helpful, and I will go over that a little bit more in our example. But when you use your graphing calculator, what you need to remember to do when you type your function into y1 is put a parenthesis around the entire numerator, and then divide by, put a parenthesis around your entire denominator. And you can use your original function to do this, or you can use your simplified function. Either one will get you the same result. Last, but certainly not least, we are going to plot all of the information you just found. Then you connect the dots within each section, but do not cross vertical asymptotes. All right, let's work through some examples. So we're going to practice identifying asymptotes first, both vertical and horizontal. So first let's think about, how do we find vertical asymptotes? We find vertical asymptotes by setting the denominator equal to 0. And then how do we find horizontal asymptotes? We find horizontal asymptotes by comparing the degree of the numerator and denominator. Remember that if the degree of the numerator is less than the degree of the denominator, then we have a horizontal asymptote at y equals 0. So numerator less than denominator, y equals 0. If the numerator is equal to the denominator, it's y equals the leading coefficient over leading coefficient. And if the numerator is greater than the denominator, there's no horizontal asymptote. So let's do these 3 examples here. For our vertical asymptotes, remember we set the the denominator equal to 0. So we will take x squared minus x, set that equal to 0. And then we're going to factor this. So we have a GCF of x, so take out x, and we're left with x squared divide out x leaves me x. Negative x divide out x leaves me negative 1. So x times x minus 1 equals 0. And then once we have it factored, we set each part that contains a variable equal to 0. So we have x equals 0, x minus 1 equals 0. So this particular function is going to have 2 vertical asymptotes, one at x equals 0 and one at x equals 1. Now let's check out the horizontal asymptote. The degree of the numerator here, we have x minus 2, so the degree of the numerator is 1. The degree of the denominator, we have x squared minus x, so the degree of the denominator is 2. 1 is less than 2, so we have the numerator is less than the denominator. If we go back to our chart here, we can see that we have a horizontal asymptote at y equals 0. G of x. For vertical asymptotes, we're going to set the denominator equal to 0, so x squared minus 25 equals 0. And check to see, do we have a GCF? No. We have 2 terms, so we're going to factor this by difference of squares. So we got x plus 5 times x minus 5 equals 0. So then we set x plus 5 equal to 0, set x minus 5 equal to 0. Subtract that 5 over, we get x equals negative 5. Add that 5 over, x equals positive 5. So we have 2 vertical asymptotes again, one at x equals negative 5, one at x equals positive 5. Horizontal asymptote. We're going to compare the degrees. The degree of the numerator is x squared, so that's a 2. Degree of the denominator is also x squared. Since those 2 degrees are are equal, I'm going to need to do y equals the leading coefficients over each other. So y equals, leading coefficient in the numerator is 2 in front of that x squared, and the denominator is 1. So I have a horizontal asymptote at y equals 2. H of x. Vertical asymptote. Set the denominator equal to 0, so x plus 1 equals 0. Subtract that 1 over. X equals negative 1, so my vertical asymptote would be x equals negative 1. Horizontal asymptote. Compare the degrees. Degree of the numerator is squared, x squared minus 4x, 14x. So the numerator is 2. The denominator is just x plus 1, so the denominator is a degree of 1. Now I have 2 is bigger than 1, so the degree of the numerator is higher than the denominator, which means there is none. So there is no horizontal asymptotes. Okay, I think we are ready to put all of this information together. So we're going to do an entire problem here. So we are just going to graph this function, but we're going to do all of the steps to go through graphing this function. The very first thing we're going to do is we are going to factor. The numerator has no GCF, so we would factor it by the AC method. I will just speed that up for you. It's going to be x plus 5 times x minus 1. The denominator does not have anything that is squared, so it just stays x plus 1. Now the parentheses I put around the x plus 1 are not necessary. I just put them there for fun, I guess. After it's factored, we're going to look for any holes and vertical asymptotes. Remember that holes happen when you are able to cancel a common factor from the numerator and the denominator. So we look at our numerator and our denominator, you can see that there is nothing in common, so nothing will cancel, which means that there are no holes. So there are none because nothing cancels. For vertical asymptotes, we are going to set the denominator equal to 0. So I have x plus 1 here. So I go x plus 1 equals 0, solve for x, so minus 1 minus 1, x equals negative 1. So my vertical asymptote is x equals negative 1. Now a vertical asymptote is going to go on the graph as a vertical line that is going to be dashed. So I can go to negative 1 on x and put a vertical asymptote as a dashed line on my coordinate plane. When we talk about the domain and the points of discontinuity, that's not listed on here, points of discontinuity, so let's just add that, points of discontinuity. Now we talked about that at the same time we were talking about discontinuities with holes and vertical asymptotes. Points of discontinuities are the x values that we have holes at and the x values that we have vertical asymptotes at. So we only have one point of discontinuity at x equals negative 1. And remember that it is non-removable if it's an asymptote, so that is non-removable. If it's a hole, it's removable. So we only have one point of discontinuity and it's non-removable at x equals negative 1. Okay, the domain is all real numbers except for the x values that we have discontinuities. Since we only have one, domain will be all real numbers except x equals negative 1. Horizontal asymptotes. Remember, we get those by comparing the degree of the numerator to the denominator. So we are going to compare degrees. And we want to do that from the original function, not from the factored. So the numerator in our original function was x squared. That degree is 2. The denominator was x plus 1. That degree is 1. 2 is greater than 1. So if you look back at your previous notes, you'll see when the degree of the numerator is higher than the degree of the denominator, there is no horizontal asymptote. X-intercepts. We find x-intercepts by setting the numerator equal to 0. So I'm going to set the numerator equal to 0, and I prefer to do that after it's been factored and canceled. There wasn't anything to cancel on this one, so I'm just going to go from my factored form. So I set x plus 5 times x minus 1 equal to 0. And then after it's been factored, you set each part that contains a variable equal to 0. So x plus 5 equals 0, x minus 1 equals 0, and that's going to give me x equals negative 5 or x equals 1. So those x-intercepts need to be written as ordered pairs. So we'll have negative 5, 0, and 1, 0. We're going to go ahead and put those on our graph. So we go to negative 5, 0, 1, 2, 3, 4, 5, right here, and 1, 0, right there. And we move on to the y-intercept. For a y-intercept, we are going to substitute in 0 for x. And you can do that from the factored form or from the original. If you use the factored form, then y will equal 0 plus 5 times 0 minus 1 divided by 0 plus 1. So that is 5 times negative 1 divided by 1, which will be negative 5 over 1. So our y-intercept will be at negative 5. That needs to be as an ordered pair. So we had 0 for x and negative 5 for y. So we'll put that on, 0, negative 5, right there. And then we're going to pick some x values to make an xy chart. So I want to talk to you a little bit about this vertical asymptote and what it's doing. I have one vertical asymptote here that's basically splitting this whole coordinate plane into two parts. So I'm going to have one branch of my function on the left side of that asymptote, and then I'm going to have another branch of my function on the right side of that asymptote. So what I will usually do is create two little xy charts, one for the left side of my function and one for the right side of my function. So that's why I've got two xy charts going for you there. So on the left side, to the left of that function, and to the left of the vertical asymptote and to the right of the vertical asymptote. So I'll choose x values from each of those zones. And what I'm going to do is I'm going to use my table feature of my graphing calculator to help me create an XY chart. So when we do that, we'll go to Y1, and we want to put the entire numerator in parentheses. So I'll have parenthesis x squared plus 4x minus 5 divide by parenthesis x plus 1. So we go to y equals and clear out whatever's there. Make sure your plots are turned off. So like if I had my plot turned on, I would want to turn that to off, because sometimes that'll mess up what you're doing in your calculator. And then I'll put a parenthesis, which is above the 8, parenthesis x squared plus 4x minus 5, parenthesis, divide by parenthesis x plus 1. And then we're going to go to the table. So I push second, and then the graph button is a table, so second table. Now mine is going to let me type in numbers, so I could like choose 99 and I could type that in. If yours isn't doing that, then you need to do second table set, so second table set, and put your independent variable on ask. I got there by second table set, change that to ask, and then go back to your table by second table. And then yours would probably be empty, but that's nothing to worry about. Just type in a number and it'll work for you. So I'm going to choose some x values that are on the left-hand side of x equals -1. So maybe I want to choose -2. So I'll type in -2, enter, and that gives me a y value of 9. So that's an ordered pair I can put on my graph at -2, 9. So -2, 1, 2, 3, 4, 5, 6, 7, 8, 9. I went off the chart a little bit. And then I could choose maybe -3. -3 is 4. So -3, 4. 1, 2, 3, 1, 2, 3, 4. I already know where -5 is. If I type in -5, guess what I'm going to get? 0. So maybe I want to choose like -7. -7 is -2.7. So if I go to -7, -2.7. Okay, I want to tell you a secret about these graphs. When they get close to these vertical asymptotes, they are going to zoom one direction or the other. They cannot cross a vertical asymptote, so it's either going to zoom up or it's going to zoom down. Since we get the general picture that this graph is zooming up, we can go ahead and draw it going towards that vertical asymptote on the up side. And then the other thing is they are generally not going to like be wavy like a polynomial. They're just going to kind of keep going in that same manner. So we just want to draw it kind of swoopy, going towards the vertical asymptote up here, and then kind of continuing in that general manner off into infinity. Then we want to do this, a similar process on the right side of that vertical asymptote. So we already know at 0 our function is down here at -5. We already know at 1 it's up here at 0. So maybe let's choose 2. So at x equals 2 we get 2.3. So 2.3. Put that on there. Maybe you want to choose something like 5 or 3 or 4. Just pick a number, type it in, see what you get. At 5 I got 6.7. 1, 2, 3, 4, 5, 1, 2, 6.7. Just pick as many x values as you think you need to make sure that you know what the graph looks like. I can tell that as my graph gets close to the vertical asymptote, it is zooming down. And it's not going to do anything crazy out here. It's just going to follow that same path. So I'm going to draw this going towards my vertical asymptote, connecting all my dots, and keeping on going. Now you don't have to fill up this entire XY chart. Just pick enough so that you have enough dots to go draw an accurate graph. So again, we did that by doing y1 equals the numerator over the denominator, and then we used second table if you want to write down to remind yourself how to do that.